Okay, let's get started. Since it's time to roll, you guys want to listen up since I want to start rolling here. It's all on tape. Well, it's on video. We're going to get through the rest of these discussions on properties of LTI systems, and then we'll look at one last topic, and then one sort of lead-in to the next chapter, and then we'll be into the next chapter. So intention is, or likelihood of getting something into the next chapter even before next week. And then we'll do a little bit more on that next week, because we won't spend a whole day reviewing for a midterm, but we will spend some time reviewing. And then the midterm will be on Wednesday. That was what we discussed on Monday. So there's two topics that are properties of systems that engineers prefer to work with, and those are linear time invariant systems. All the linear circuits modeling that you'll be doing when you take 2205, and a lot of the circuits modeling that's done in electronics is all under the same premise, linear time invariant systems. The modeling is a lot easier, the math is easier, the behavior is more of what we desire in most cases, but that's not to say that time-varying systems don't count, because they do, and nonlinear systems are also very important, because there are certain times when we want a nonlinearity to be present in a system. Was working on a lab experiment for the communications lab this morning and the last few days that involves exactly a nonlinear circuit, and it's a lot harder to analyze it, and its behavior is a lot more confusing to see on the instruments in the lab, but it's part of what makes radio work. But the two properties that make up a linear time invariant system are linearity and time invariance. And last time we looked at the time invariance examples, a couple of those. And today we're going to look at linearity, and then we'll go to the example sheet and we'll work out the proof for a couple of examples. And then if you go look at the assignment sheet, set number 7, it's got more problems that you get to work on. And then, as you might well imagine, the quiz for Friday will be some type of problem along those lines. So the time invariance property is summarized in this figure right here, and also the proof setup is in this figure. The time invariance property, as we talked about last time, says that for a system to be time invariant, it must be that I can apply the input now or at some other time, shift and not, and the output will be the same as if I apply it now, taking into account the time shift. So the way this figure was set up, clear off the crud, put down a new layer. If we delay the input by n naught, we get some output W of n. That's for the delayed input. And then we compare that to the input coming in at the present time, undelayed, and that produces our ordinary output Y of n. If the system is truly time invariant, W of n should equal Y of n shifted by n naught samples. And what that is telling us then is that the system behavior is identical when we apply the input at the present time, or sometime in the past, or sometime in the future. That's what the time invariance means. And it seems kind of like a fancy abstracted name, but remember what I said last time, a good practical example is to think of some system or device where it changes with time. It ages with time, it changes with temperature, and temperature changes with time. Anything that would cause some property of a system to change with time would violate the time invariance idea. But most systems, like think of analog circuits, which you'll be getting into, if it's got resistors, capacitors, and inductors in it, ideally those components should stay the same. They shouldn't change over time. but what's in reality true of virtually everything that we make. It gets old and decays and changes. I mean, our bodies are good examples of that. So electronic circuits age over time. If you're a digital person, you'd say, but digits are always zeros and ones. They never change. But, you know, you've got to have a lot of digits to make an analog waveform, so there's some inefficiencies in there. And then there's also the analog interface circuits that'll change. But time invariance is not something where you have to consider it over, you know, decades of time. Time invariance to be good just has to be over the interval that you're interested in processing the signals. So maybe it does change over a period of a year or more, but over a few milliseconds, it looks time invariant. So that's another aspect of the time invariance idea. So we did a couple examples of that, and we'll come back to some more in the worksheet. The other big property that we like to have in systems is linearity. And linearity is another way of saying superposition holds. And superposition holding means that if I apply an input x1 to the system and it produces y1, and I apply an input x2 to the system and it produces y2, if the system is truly linear, then I can apply an arbitrarily scaled version of x1 by alpha, an arbitrary scaled version of x2 by beta, and the new output, y of n, must be equal to alpha times the individual y1 that I got by applying x1 plus beta times the original output I got when I just applied x2. So if that seems kind of strange, a good example of that, and the example I sort of promised you last time, a karaoke machine, for example. I don't do those things, but I know they exist, and I know bars and other places have activities like that, right? So how does that system work? Music plays, and then somebody has a microphone, and they get to superimpose their voice over the music. Isn't that the basic idea? So that's an example of superposition, and we hope that that's a linear system so that the music can be really loud, and then the person mixes in their microphone input. Like suppose the music is coming through with some gain or volume level as x1 into the power amplifier, and the microphone is coming in through another gain setting beta as in signal x2, and then we hear it over here as a composite output. If we tested the system with just the microphone at a reasonable level with no music playing, we'd say, good, it sounds great. Turn the microphone level down and just play the music, sounds great. Now we superimpose both of them together to form this composite signal, x of n, which is what would be happening in the live action, and the output sounds not so great. What would be happening there? What would be a likely cause of that? This is kind of checking your intuition on audio systems. If you've ever played with a mixer in an audio system, what happens if you turn the volume up too far in any stereo system? It starts distorting. So linearity, the assumption would be if I'd have just the microphone and the person talking, it's clear. If I have just the music, it's clear. But if I bring the two of them together, now the net signal that's driving the audio amplifier, x of n there, is going to be what? Bigger, right? Because I've got two signals coming together. So there's an increased likelihood that I'll start driving the amplifier stage into distortion, and it will sound distorted. That's maybe doesn't sound very impressive, but that's a tendency I think people would have. You know, the music is already loud, so let's crank the gain on the microphone up louder to make sure that voice can be heard, and then you end up with a lot of distortion because the system can no longer handle that superposition. So that's an example of a nonlinear system. But if you were to just back the gain levels down on both of the inputs you're mixing in, you could maintain an undistorted output. You just can't keep raising the power level indefinitely, and that's true of any electronic circuit. You can only provide so much total power output. So the reason why I mention that is because I often hear audio systems cranked to the point of distortion, or people seem to enjoy talking into a microphone through a loudspeaker system so that it's just pure distortion, and if they just back it down a little bit, the voice might be more intelligible. But I think having it being distorted maybe is just an idea of, I want to really make sure everybody knows I want you to hear me. I want you to hear me not so loud, maybe more distorted than anything else. So how do we establish linearity? In other words, the idea that no distortion is going to occur. We have another kind of a model that we go through, and this is the book's idea. So the idea, again, is set up kind of like before in the time invariance case. It's two block diagrams. So one is where you bring the individual signals through one at a time. X1 comes through to produce Y1. X2 comes through to produce Y2. Then you apply the individual gains, alpha and beta, to get your composite W sub n. And then you go ahead and take the complement of that, or not really the complement, you just switch it up and say, let's mix X1 and X2 together with gains alpha and beta and apply that composite to the input. If the system is truly linear, then these two have to be equal. But you can see how in the case of the karaoke machine, how this problem arises. The upper block diagram is not what you want to do in the actual operation. You don't want to just have the music or the microphone set up. You want to have both mixed together. So this is the live action scenario, but you do an initial test and it works great with one or the other. When you mix them together, then it doesn't work because you're overloading it. For a system to be truly linear, it has to hold. Both conditions have to hold. I mean, they have to be equivalent. And the linearity idea is just, I don't know, I could say it's awesome and you wouldn't believe me, but it's what makes everything work. We can superimpose signals. And why do we like to superimpose signals? It's because we model something with just one signal applied. We fully understand that, then we model it with another signal applied, then we say if the system is linear, we can just bring them together, and we already know what the response is going to be because we understand that it's just going to be the sum of the outputs. We don't have to do our initial analysis. And in circuit modeling, that's exactly what you do. In the convolution sum formula that we were using last week in class, linearity was used in that. I guess, by the way, that convolution sum formula to get the output, to get the convolution of two signals, say an input and an impulse response to form the output, that relies on a linear time invariant system. That whole model and whole math setup is based on having a linear time invariant system. So I guess you could then back up from there and say, well, that must mean that the FIR filter we started talking about at the beginning of this chapter represents a linear time invariant system as long as it has constant coefficients or constant B sub k values. And that's absolutely the case. That's what it is. So we kind of avoided some of the mathematical fine points in the beginning so we get some of the mechanics down, and now we're coming back and looking at some of these properties. So let's take and revisit one of the examples that we did the time invariant study on. Remember, this system from Monday, was this time invariant or time varying? Remember? For a system to be time invariant, the properties of the system must stay fixed over time. This looks like a system that has a time varying gain because of that n sitting in there, right? Remember, I made it analogous to a time tick or a clock internal to the system. Or another way of thinking of it is, if you're just drawing a block diagram with an amplifier, a triangle is generally an amplifier. generally you think of an amplifier as having some gain A, so X goes in and Y comes out. But in this case, that A is actually a function of our time variable N. So that definitely, in big, bright boldness, says the gain changes constantly with time. It's constantly ramping up. The more positive we go, or ramping negatively if we go back in time. But what about linearity? Is linearity going to hold? Well, we let our system operate on, so this is the response we get when we apply x1 by itself. So x1 applied to the system comes out all by itself as n times x1, and x2 applied to the system comes out as n times x2 of n. We're doing this first block diagram up here. We're applying the inputs separately and getting the separate outputs, n times x1 and n times x2 in this case. And then we're going to apply the alpha and beta and then add them together to form W of n. And then down here we're going to apply the input all at once. That's the composite input, alpha x1 plus beta x2. Let the system operate on that, and that just multiplies it by n. So if we want to compare these two guys together, they're identical, aren't they? I mean, the math says that they're identical. Again, kind of like in the proof of the time invariance, if it's a simple enough example, you have to do a double take on it, because if you just glance at it, or if you're in a hurry, you're going to say, what did you do? You didn't do anything by me. You see what I'm saying? So what you have to do, and what you're going to have to think about, is this picture. We're definitely doing different things if you go back to this picture. The first picture says we apply x1 and x2 just to the system separately to get y1 and y2. Then we mix the outputs together through the alpha and beta gain scale. Whereas in the second one, we mix the inputs together up front, the karaoke example, I guess you can refer back to, and then drive it through the system. And we see if the two results are identical. So in this particular case, the system's definitely linear because, you know, if you wanted to drive this down further, you could, about all you could do to drive this down further, you could just pull the alpha and then write it as nx1 of n, and then put a parenthesis around there differently. Then you could say, look, it's alpha times x1 applied to the input, which was nx1, and it's beta times nx2 applied to the input, and that was identical to the W of n output. I guess I'm thinking of something that I could say. I'm not sure if I should do this or not, but when you take calculus, have you ever done any proofs in calculus or any math class? Simple proofs? You're trying to prove something. Mathematicians have language that they like to use when they're doing math proofs. And when I had advanced calculus and real analysis in graduate school from mathematicians, one of the, besides learning the special sign language that they have, that you probably haven't learned too much of that, but you've learned a little bit of it, I'm sure. They also, I say sign language, it's little symbols. They have a symbol for therefore. You know, the therefore is the three dots, right? But then there's a such that and a there exists. Ever seen those symbols before? Okay. But another term that they like in their proof language is the word clearly. That's a pretty powerful word. If you get so far in a proof, like we did right here, and just looked at Wn and Yn without doing any more writing, your eyes would just say clearly W of n equals Y of n, and that would be not a stretch of the imagination because you can see it there on the page by just thinking the algebra in your head. There's other times, though, when clearly is more of a stretch. So if you're writing out a solution to the quiz or the midterm next week, and you hardly write anything down on the page, and then you just say clearly it's linear, and that's all you do is just say those words, but don't write anything or have anything on the page to kind of back it up, I'm going to be kind of irritated about that. So that's why I hesitated. It's okay to use the word clearly, but it's got to be clear to you, and if it's not clear to me, I'm not going to accept it. And I was bothered by that when I had my advanced calculus, because the professor said it's okay to use it, but then what we had to do, he had us up at the board always doing proofs, and the rest of the students in the class were watching us, he was watching us, so you couldn't necessarily get away with anything unless you could get everybody in the class on your side, that if it was clear to you, it was clear to them, and it would overrule the professor, but that didn't work either. But it was still sort of a game in a way. But of course, if you say something is clearly true and it's definitely false, then it's like you just put your foot in your mouth big time. So just watch how bold you may get. It could get you into trouble. Okay, another example is y is equal to ax plus b. This is kind of a classic example where linearity fails, and if we wanted to draw a block diagram of that using our amplifier model, we could say it's composed of an amplifier gain A, and then we have a constant summed in B that's part of the system. So we can see the signal flows through the upper path, picks up the gain of A, and then summed onto it is a constant of B. And in electronics, this is fairly popular because when you build up amplifiers out of active devices like FETs and bipolar transistors, you end up having some bias present just because of the electronic circuit design. So the fact that there's a B added on is not all that surprising. So the way you'd prove this then is you would apply the individual inputs to the system. So here's the application of x1 produces at the output a times x1 plus b, and then we apply the second input to the system and it produces a times x2 plus b, and then we apply the gain scales after they come out, alpha and beta, and then I went and did some factoring on that. So I got an a times alpha x1 plus beta x2, but then I also get a constant term out over here, b times alpha plus beta. Interesting. Don't know if it's going to work or not, but we have that variation. Now we apply the composite input that's been superimposed through scale factors alpha and beta, so that goes into the system as a composite. It picks up the system's gain of A because it's flowing through this upper path here, and then the B gets added on as the bias term. Now look at what happened that's not good. Here we have B times alpha plus beta, and down here we only have B. So the buzzer goes off, as in the foul buzzer in a basketball game or something. It's no good. It's not linear. And you see why? Now, what could we do to make this system linear very easily? If we had control of it, what could we do? We don't have control over alpha and beta because those are, for linearity to hold, by the way, I didn't say it, alpha and beta have to be any finite numbers. So we can't rig it up by making alpha plus beta equal to 1, for example. That's not valid because it has to work for any alpha and beta. So what could we do?
Bias the signal prior to adding alpha and beta.
Okay, that'd be one approach. What would be a better approach that's more logically from the math sense is just simply set B equal to 0 somehow or another, manage to make it equal to 0. And the way that's done in an electronic circuit, we could use something called a coupling capacitor. So if we were, I'll just show a simple little active circuit. I could show it as a transistor or a FET. I guess I'll put a junction FET in here. I'm more of a transistor person because that's what I grew up with. So if this was a resistor right here, called the load resistor on an amplifier, and there's some biasing in here, and the upside down triangle, it means tying it to ground. There's going to be a DC bias that's going to be added onto this output because there's going to be some current flowing down through here, which is going to put a steady bias voltage on there. Plus, the signal that comes in here, like that, is going to get amplified up into a much bigger, say, sinusoidal signal, but it's going to be riding on an offset. So rather than if this signal was riding about 0, this one's going to be riding about some DC value, which is 0, and then some positive value. But if we put a coupling capacitor in this whole setup, which is more typically what would be done, and we first learn about this in Electronics 1, call it C sub C for coupling capacitor. Then you block DC, and then the waveforms right about 0, both from the input side and the output side both. So you can make it look like a linear system then. Okay, another case of interest, and this is just sort of backing up since we've discussed the FIR filters already, and I've already said that it must be linear in time invariant. We can now take our FIR filter and just establish that it is indeed linear. And the FIR filter model, remember, was Y of n was k equaling 0 to n of bk times x of n minus k. So that's the input-output relationship or difference equation for the FIR filter. So now we apply the same modeling technique for the time invariance. In the time invariance case, we'll let the input be delayed by n0 samples. So the input is V of n, and V of n is a delayed version of the input. So V of n minus k goes in there in place of x of k. And then once I rewrite the equation, on the far right here, I'm going to replace V of n minus k by x of n minus k. So where I had the n before, I replace it by n minus n naught. So I would have originally started off by writing this as n minus k, and then, just like I did, minus n naught, and then I can group the parentheses accordingly. So when I rearrange it, so I have n minus n naught minus k, then I can see that this just looks like, I don't think I did this on the next line. I guess I did. Never mind. So that's W of n. I was going to skip a step, but I have the next step in here. So that's W of n, and then the next part of the time invariance proof was to drive the input in on time and form Y of n, and then take Y of n and delay it by n naught samples. So if I delay it by n naught samples, that replaces the n in here by n minus n naught, and those two are now equal to each other. So time invariant, without writing it out. So the system is time invariant. What could easily destroy the time invariance would be if these coefficients somehow or another, if the bk's here were bk of n, let's say, they were a function of time, then things would not hold up. And in what's called an adaptive filter, that's the case. You learn about adaptive filters when you take some of the classes that I teach, or maybe Dr. Plett in the control systems areas might teach, but definitely in classes I teach, you bump into adaptive filters. Remember I said adaptive filters are part of the noise canceling headphones or various other applications in communications and signal processing. The noise canceling headphones is probably the most dramatic one, though, that I can think of. If you own a pair, if you spent the money, that is. They're expensive, but does anybody know what I'm talking about? Does anybody own them or tried them? Just go to Best Buy sometime. They have a nice display for the Bose headphones where you get to try them out, and then this fan is sitting there to represent the noise inside an aircraft, and that turns on after you start listening to the music, and then it's making all kinds of racket, but yet you don't hardly notice it. Or if there's people around you talking, you don't hear them hardly at all either. It's pretty dramatic, but they're $300, and you got to hold on to them. I've just about bought them several times, but then I say, $300, and I could screw up and lose them or break them, and then what? So then I say, maybe it's not such a good idea. So when I listen to my music at home, I also say, my wife would really think I'm tuning everything out, and that would probably be rude. So if you're not married, though, you can probably have them and not offend anybody. That's just a thought. Okay, what about linearity for the FIR filter? The linearity proof just works the exact same way. We go and look at the definition, and we'll get y of n first. Y of n means we're going to apply at the input the composite. And if we break that down then, in other words, we use the linearity property of the sum. If that's the composite input, then we see how it fits into the difference equation. We can just break it apart into two sums, and the beta and alpha can factor out in front of the sums, and then we've immediately established without even going any further that that's just alpha times y1 plus beta times y2. So superposition or linearity holds for the FIR filters we've talked about. So the conclusion is FIR filters as we've described with the constant coefficients is an example of a linear time invariant system, and it's the most important example that we'll have pretty much for the entire semester, is that the filters we're going to talk about are always going to be LTI. And for people that do software, that just says the coefficients are stored in firmware, in a lookup table or something, somewhere in the system, and they never get changed. But of course, if you want to write flexible code, you can allow the operator to download some new coefficients to change the characteristic of the DSP-based device, but they would stay constant during the operation of the device. If you made them time varying, then you'd have a time varying system. Okay, at this time, we're ready to go study some more things about convolution, but before we do that, we should go over and look at the example sheet.
Any spares up there?
Yeah, they got passed around. They're floating around somewhere. This example is very easy to me. I look at it and I say, there's nothing to it, but to walk through the arguments, that's what we have to do. So that's our input-output system. So one of the things that you might do is draw a picture of what's happening. That might help you understand whether or not it's linear or time invariant. Basically, we've already worked an example like this. It's just had a slightly different variation on it. But if I was to draw a block diagram for it, I'd say it looks like our signal is entering a system that gets a gain applied to it, and that gain is a function of time. So right away, what's the bad news about this system? It must be time varying, right? But if we wanted to actually prove it according to our proof setup, we would get W sub n, we would delay the input, right? According to W, we would delay the input to form W sub n. So if we delay the input, W sub n would be, the input would come in delayed by n naught. And then, of course, that weight, time varying weight gets applied, 0.2 pi n. And then the other part of the proof says we then apply the undelayed input to form y of n. That would be x of n minus x of n, times the time varying gain. But then what we want to do is we want to replace n by n minus n naught. In other words, we want to shift the output of the system. So first we shift the input and get W of n, and then we take the undelayed input and apply it, and then shift it at the output. So y of n minus n naught is going to be what? X of n minus n naught. And here's where things fall apart. 0.2 pi n minus n naught. Does that look right? Because we're picking the entire waveform up at the output and delaying the entire waveform by n naught. Whereas in the first case, we just delayed the input by n naught. The system just sat there and said cosine 0.2 pi n is what I do all day long. Has no knowledge that the input has shifted. See that they're not equal, right? The common mistake that people always make in this, whether they be in this class or even in the graduate signals and systems class, is that you think when you're delaying the input, which is in calculating this line, that you're entitled to delay that, replace that n by n minus n naught. But just think about it. Why don't you do that?
Because you're delaying it before it goes into the system.
Right, and the system doesn't know what's going on with the input. It's just doing its thing. This thing right here is a property of the system. If you go ahead and delay the input or advance the input, the system doesn't care, but it definitely doesn't know about n naught. It's like it's dumb. It doesn't know that. So don't fall into that trap of thinking that the system time clock gets shifted, because it's just humming along with its own beat, basically, time variable. Okay, what about linearity, since that's the next one? Does a time varying gain destroy linearity? We've already done an example, but not this exact example. Let's see. So the linearity idea says that we first applied the inputs individually, so we were to calculate W sub n as equal to alpha times the input applied separately, which would be the x1 of n times, and that picks up the cosine 0.2 pi n. Then we apply the second input separately, so that gives us x2 of n times the cosine of 0.2 pi n, right? That was the approach. Apply the input separately, get the output. So this thing right here in the braces, this is y1 of n, and that's y2 of n. The second half to get the proof is to apply the composite. So the composite is basically where we plug in alpha times x1 of n plus beta times x2 of n as the input. So that goes in all at once, and then it picks up the time-varying gain of the 0.2 pi n. So now if we work through the algebra on that, what do you see? It agrees, right? It works. It almost seems too easy. So I could make it a little bit more difficult, but actually I can't. There's not a whole lot I can do. There's only a few different things that I can try. If you're thinking back to the example that we worked in the notes just a few minutes ago, there we had the example, y of n is equal to n times x of n. That was a time-varying system, but it was still linear. So the key is that n is behaving the same way that the cosine of 0.2 pi n is. It's just a time-varying gain. And a time-varying gain doesn't destroy the linearity property. But what happens if I was to tweak this thing and put something out here like u of n? That's this unit step function, right, that I defined in the homework problems, and the book has it defined somewhere or another. What do we know already about adding a constant onto our signal? What did that do to the linearity? It destroyed it, right? When b was non-zero, when we added a b on, that destroyed it. So we can think of u of n as like we're applying a constant onto the system. Now it's conditional. It's 0 when n is less than 0, but for n greater than 0, it would be present, and that would destroy linearity. So overall, the system would be nonlinear, because even though it's linear for n less than 0, when n got to be greater than 0, it would be nonlinear. Another thing is, if I was to take the n off over there, now what happens? We don't have a time-varying gain on x of n, but is the system got a time-varying behavior to it? It does, because, yeah, that bias, that u of n is a bias which changes with time. Some of the time it's 0, some of the time it's 1. So that also messes up the time invariance property. I guess maybe the moral of the story is, of the cases that I could have you work on a quiz or on the midterm, they're all going to boil down to basically the same idea. They'll just be disguised in a slightly different form. Rather than being n, it could be cosine or something, or it could be n squared, n cubed, and then I could add a constant on, a time-varying constant. I mean, there's just a few permutations to this whole thing where you need to recognize what's going on. But getting back to the clearly idea again, if you're proving it and you think this is just like example such and such that we talked about in class, you can't, in your proof, you just can't say, remember at whatever time it is, at 2:23 or whatever it is right now, we did this example just like this because you had this photographic memory, and you say, clearly because of that example, this is of the same form, and therefore it's time invariant or time varying. That's not going to sell very well. You have to actually go through some of the details. So the best approach is to take the book's approach, which I put in the notes, which goes through the proof setup. So by proof setup, I mean you go back over and we're driving it through these two block diagrams. So for time invariance, we're doing this setup. We're saying we're going to establish that W of n and y of n minus n naught agree. So that would be the proof setup for time invariance, and then for linearity, you're driving it through this setup right here. And just another point to make note of, if you're trying to prove something is true, you have to do this for any value of alpha and beta. It has to work. Likewise, in the time invariance proof, this has to work for any value of n naught, any value you choose. Now, on the other hand, if you suspect a system is not time invariant, you could pick just a particular value of n naught and establish immediately that you have a contradiction, or if you have the scenario where it doesn't hold. So that could streamline the proof process. But if you're going to try to prove that it's true, you've got to show it's true for any value of n naught. Likewise, in the linearity, if you think it's not true, you could just prove it for a particular value of alpha and beta, like 1 and 2 or something like that. You don't have to establish it for any value of alpha and beta. And of course, in real processing systems, whether they be digital or analog, alpha and beta have to be bounded in some way. Because in the karaoke system, it was making alpha and beta too large, which led to the distortion in the output, right? The power amp got overdriven and started distorting, or maybe the speakers started ripping apart. That also creates distortion. When the speakers start banging into the ends of their excursion, that'll make a distorted sound. In the digital system, the killer would be finite precision arithmetic. You've only got a certain dynamic range, and you can only represent numbers of such and such size, so that will limit what you can do. Does anybody have any questions?
So you're basically saying for some reason, if we can't prove it, mathematically by working out the equation, just prove it for certain values of alpha and beta.
Disprove it. Yeah, disproving just requires finding one counterexample where it doesn't work. And I'm sure that's something you learned in math too. I remember again from the same professor that I had the advanced calculus from. He had a really thick Missouri accent because I went to graduate school in central Missouri at Missouri Science and Technology, School of Science and Technology as it's called now. It used to be the School of Mines there. So to me it was comical because I grew up in Wisconsin, so the southern twang or drawl and all that other kind of stuff just kind of grated on me for a while. I couldn't quite take it, but I realized some of you have it because you've grown up in different parts of the country. And you think people from Wisconsin sound nasally and they're all cheeseheads, right? Because that's where I grew up. It was very close to Green Bay. At any rate, he was pretty comical, but one of his favorite sayings was, the obvious is often difficult if not impossible to show or prove. So when you're saying mathematically, that comes to mind that it's so obvious, but I can't put it in mathematical terms, so you're stuck. And if it's proving something, you've got to do it in the general setting. But fortunately, if it's disproving something, you just have to find one counterexample and then you're done. The best way to take it, though, if you're in doubt, is to use these drawings that are in the book and take that tact on it, because that will hold up either direction. It will work. Okay, the other half of the example sheet we have to go through a little bit more before we can get to that. So convolution in LTI systems. This is going to kind of get some summary stuff going about what it means to do a convolution sum to get the output from the input and the impulse response. So this is going to establish that convolution sum formula from first principles and using the properties we've just worked from. So for starters, we can take any sequence x of n and we can expand it on the right-hand side here by just taking all the values in the sequence and placing them on the time axis using a time-shifted delta sequence, and then letting the amplitudes be x of L's. Now you can look at that and say, that seems like a lot of work when x of n is just a sequence that rolls off all by itself, but it's important in the next step, in step number 2, to be able to say we can take the individual values of x of n can be cited on the time axis as, that value would be, say at 1, that value would be x at 1 times delta of n minus 1. And then we can do that for all the other values. So then what does time invariance mean? Time invariance would apply in our proof of our LTI system that the impulse response should shift accordingly with n naught. So if delta of n minus n naught is input to an LTI system, that says it produces at the output the impulse response h of n minus n naught. So in the above expansion, x of L times delta of n minus L becomes upon going through our LTI system, if that's input, then the output is going to be x of L times h of n minus L. In other words, we just put in one sample value of the input, namely the value, say, at n is equal to 1, drive that through the system, and it produces the impulse response. Because that's just like one delta going in. It produces the impulse response, and the corresponding amplitude is x of L. So now we can go ahead and use linearity. We've actually already used linearity to some extent with the x of L on there. But we're going to now operate on both sides through the system. So we're going to write the input as this decomposition into the constants x of L times the time-shifted deltas, and then operate through the system. So this arrow here means we've come through the LTI system with this input. So this input drives in, and then it produces at the output x of L, h of n minus L, because individually we can apply those to the system and get the corresponding output x of L, h of n minus L. But if it's linear, we can apply a whole collection of those things and get at the output the superposition of all the individually applied inputs. And that, because of linearity, is y of n. It's as if we applied the composite input from the get-go. It's the same as superimposing all the individual inputs. So this hopefully sets into your mind the importance of linearity and time invariance. We can build up the output in terms of the impulse response and samples in the input using this convolution sum. That's really where it comes from. And if you're wondering why the time flipping occurs on there, it's because when we originally expanded the input, we had to represent it as time-shifted versions of an impulse, delta of n minus L, and then when we applied the system operator to that delta became the h of n minus L, and we were having to evaluate over all possible values of L that the sequence exists for, and so we end up with this convolution sum formula that we played around with starting last week. Sound reasonable? So when you think of an output of a filter, it's like I'm superimposing all of the time-reversed impulse responses that have been shifted out to different locations, and then apply a gain scale on each of those, which is whatever the amplitude of the input sample was at that instant, and then add all of those up, and that becomes the composite output. But when we think of the mechanics of it, of course, in this equation 530, we did that with the table method, right? We set the table up where we actually had h of k, and we had x of n minus k. So that's sort of a missing piece to the puzzle. This looks like something different than what we did before. So what we have to do now is show that they're equivalent. In other words, we have to show that it's equivalent to this expression right here. And of course, when we worked this before, we didn't have this go from minus infinity to plus infinity, and the reason for that is that the impulse response was an FIR impulse response, which started at 0 and went up to n, right? So we just truncate it because the h of k there is finite, so the sum limits are constrained by h of k, the impulse response, not having support over the entire axis, but still the same idea. So this equation 531 takes the previous convolution sum and sets its limits up. In other words, if I have it running from minus to plus infinity, but yet I know this is finite support, the support for that h of n minus l has to be where n minus l runs between 0 and n. Because that was the definition of the FIR filter we were dealing with. So down here, I guess it was M. I knew it was M, not N, but at any rate, its support interval is 0 to M for N minus L, and then just swirling that around in terms of L, we rearrange that inequality down here to just say L needs to only run from N minus M up to N. So that modifies for the FIR filter that first convolution expression. And now we can just do a change of variables in this convolution sum of 531 to get it to look like this formula right here. That changes back to an M. And this is interesting. It just tells you that something that we haven't had to do yet, but in calculus you do change of variables and integrals, right? Sometimes that makes life easier to change variables, substitutions, and all that other fun stuff. In a sum formula you can do a change of variables too. So here we're just going to replace n minus l with k. So we're going to do that substitution in up in here. And if we do that, then what does L become? If k is equal to n minus L, where we have L is we replace it by what from the algebra here? Just solving for L, what do we have? Is that right? So that means n minus k goes in up here, and then just like in an integral, when you do a variable substitution, what do you have to do? You also have to take care of the limits, refix the limits. So here, the lower limit on L was n minus m, but now under the change of variables that k is equal to n minus m, we take n minus m. So the lower limit becomes m, and the upper limit in that sum is little n. So little n gets replaced. L is equal to n implies k gets replaced by n minus n, which is 0. So the upper limit is 0. So that brings us down to here. But then because a sum doesn't matter the order that we do it in, we can just flip it to go from 0 to n rather than from m down to 0. In an integral, what do you have to do if the limits are order is reversed? You should know this, right? If you want to change the order of the limits, what do you have to do? Negative sign, right? In a sum, it's so blatantly obvious that you don't worry about it. But in calculus, it's because you have that differential, and that flips it around. I guess I like this better. But again, if you write code and you do k++ or k minus in a for loop, let's say, it's like I can count up or I can count down, and that's kind of what that tells me. I just don't like the idea of seeing in a summation summing down. I always think of summing up, but it works either way. Okay, another little aspect, a little thing to talk about is looking at convolution as an operator. The convolution sum said we slide one signal past the other and form the sum of products. The symbol that I introduced earlier was this asterisk. This is kind of the universal symbol. If you're taking two sequences and throwing this operator in between, this implies or means convolution. So the resulting sequence in this case is y of n. But if we view this as an operator, then we can observe that there's properties of this operator. One of the special properties is what happens when you convolve something with a delta sequence. So if you take x of n and convolve it with a delta sequence, you can put this in your memory banks for later, but the proof of it would be to go ahead and run out the convolution sum. So we take x of k times delta of n minus k, but now it's going to be n minus n naught minus k, and then do that sum. But this sum is very easy to do because as k sweeps along from minus to plus infinity, what one and only value pops out of this sum? Remember, the delta sequence is equal to 0 unless what? The argument is equal to 0. Remember, the delta turns on when its argument is equal to 0. So unless n minus n naught minus k equals 0. So when you set that equality up, that says when k is equal to n minus n naught, that's the only value that comes out of this sum. Isn't that a great relief? It's like, I see a doubly infinite sum. How am I going to do this thing? The delta function makes it easy. You just look for the one and only value that comes out, and you can think of k as starting at minus infinity, which I think of as being like down at the center of the earth, way down there at the bottom on the floor or in the basement, summing up, going all the way up to the ceiling or infinity. And at some value, as k goes stepping along like that, it hits that one value, in this case n minus n naught, where it turns on, and then that multiplies x at that k value by 1, and that's what comes flying out. So the thing to remember about the convolution with the delta is it's called the sifting property. When you convolve x with delta of n minus n naught, it sifts out one value, or it sifts out the waveform at time shifted by n naught samples. So it effectively imparts a delay of n naught into the waveform. So it makes the output come out as n minus n naught, or n naught samples delay. Another property is commutivity. You can change the order. X convolved with H is H convolved with X. And this was useful and could be useful in actually just proving the different forms of the convolution sum like we were already looking at. So this little exercise here was just a repeat of what we had already been doing. The two different forms of the convolution sum, this one right here and this one right here, basically are just demonstrating that X convolved with H is the same as H convolved with X. In the table method, we were using this form, right? Because H stayed fixed. and X is the one that flipped and got slid along. But you could do it using that form if you wanted to. You could have X fixed and let H flip and slide along. You're going to see when you play with that software on Friday in the lab that either view could be taken because that animates the process for you. Then the associative property also holds. So if you've got two things convolved, you can do the first convolution with x1 and x2 and then convolve a second time, or you can do the x1 and x2 and x3 first and then convolve with x1. Now an application is what's called a cascade, and this is timely. It's on the worksheet, could be on the quiz on Friday, and it's in this lab that you're going to start on Friday too. You probably won't get to it until next Friday, but cascading is when we put two systems one after the other. You can think of it as, again, from an audio electronics example, having a preamp and having a power amplifier, or having two different type of gain stages, one being a filter, another being an amplifier. So in this case, we're just modeling as if it's two LTI systems in cascade. So, and this is part of systems design where you think of, I'm going to cascade a filter, another filter, an amplifier, and basically take advantage of linearity. Linearity will let us do some powerful things. So in this case, we're interested in what is the response of the cascade. So we have H1 is the first system's impulse response, and H2 is the second one, and W of N is the interstage point. What you're going to be doing in the lab is W of N will be a waveform that got distorted by the filter number 1, and then filter number 2 comes along and tries to undistort it. Can you think of an example in practice where that might be valuable, where one system causes distortion, not because of any of your own doing, it just happens, and then when you receive the signal, you'd like to try to undistort it? Microwave, okay. Yeah, not a microwave oven where you destroy something by heating it. Yeah, in radio, it absolutely happens. In all of our cell phones, we have some form of equalizer. The signal gets distorted because of the multipath. Remember we were talking about multipath a while ago? So our cell phones sense the environment, and they actually work with a training sequence in some cases, or in other cases, more or less an on-the-fly measurement. But suppose it's a training sequence. We know what the undistorted waveform looks like, so there's a training sequence embedded in the waveform, and it then can design this LTI system number 2 to try to remove some of that distortion. And it does that for every frame of data that's sent. So that way, if the environment changes, it always is trying to get the best performance. And that then creates an adaptive, what's called an adaptive equalizer, or some sort of adaptive equalization technique. Another example might be in image processing. If the image is slightly blurred, like in Photoshop, you can use some sharpening masks and other things on images. You are going to be doing something with the eye chart. You're going to have an eye chart that you're going to be playing around with, and you're going to distort it, and then you're going to try to undistort it. So you're going to be looking at this idea in both a one-dimensional filtering case and then a two-dimensional case in the Lab 7. Okay, what we'd like to do is see what is the cascade response. In other words, it turns out that, I'm just about out of time, that this thing can be cascaded up into being some equivalent impulse response H of N. So if we look at it, W of N will be X of N convolved with H1, and Y of N is going to be W of N convolved with H2. So if we stack that together, we take X of N convolved with H1 is Wn, and then that gets convolved with H2, and then we use the commutative and associative properties, and we can drive down to the idea that the equivalent impulse response is just H1 convolved with H2. And then because of the associative property, or the commutative property, we could change the order. We could put H2 first and H1 second. So the bottom line is when we have a cascade, the impulse response is a convolution of the individual impulse responses. So I have an example of that right here in the notes that's all worked out, and then this was the second example in the worksheet. So in this worksheet example, there's two difference equations given describing two different systems. So just from the difference equations, this one has corresponding to it an H1 of n, and this one has corresponding to it an H2 of n, right? So what is the impulse responses? This was a question that came up in the quiz last week. What's the impulse response here? Another way of describing this would be the BKs for this would be, 1, 0, 1, minus 1, right? And then for the second filter, H2 of n would be delta of n plus 2 delta of n minus 1. And then the BKs for that filter are 1, 2. So how are we going to convolve these two sequences together? We can do the table. We can do something similar to that. So if we wanted to do the table, we'd maybe put 1 and 2 in the first top row of the table, and then we'd have to start putting our time shifted and flipped versions of the second waveform in the other rows of the table. But as a starting point, we would say, just like we've done before, this is going to be this starts at n is equal to 0, and this starts at n is equal to 0, and this is n is equal to 3, and this is n is equal to 1. So what do we need to calculate the output over? 0 to 4, right? The sum of the two start values plus the sum of the two end values. So we have to have 4 different entries in here. And the first one would be 1, 0, 1, minus 1, just stretching it out backwards, and then march that guy across. And we have to do that. So this would be for n is equal to 0, n is equal to 1, n is equal to 2, 3, and finally n is equal to 4. Instead of it being y out over here, now it's h, or call it h3, let's say. h3 is the convolution of h1 with h2. I'll put up the solutions to this, but I'm pretty confident you know how to do this already. So the quiz will involve some mixture or solo version of either of these two types of problems. This boils down to the calculation from last week, but you have to be able to discern that out of how the problem is set up. But maybe I'd just give you a picture of the impulse responses too. We're just finishing.
I'm sorry.
Anybody have any questions? And we'll start lab 7. And if things go really well, let's put it this way. I'm actually almost certain, I'll just announce this right now, that next Friday we won't have a quiz. You'll have the midterm on Wednesday. So the deal is, if you are confident and comfortable with lab number 7, you can come in and spend time and get sign-offs done, or if you're ahead or whatever, if you want to go out for spring break early, you don't have to come to lab on Friday next week. Does that sound good? I don't know what else I can do, but that's something. So.